What up, guys? Today I got the Quantum Mechanics 3rd edition by Mr. David Griffiths. This is a very interesting book. This is an introduction to quantum mechanics, standard text for most introduction to quantum mechanics courses. David Griffiths also has a crazy electromagnetism book that most universities use. And when I first studied quantum mechanics in university, this is the book I used. So I wanted to go through it really quick. Last time I took it was maybe 3 years ago. And I'm going to be making some videos about this book, so I wanted to sweep through the table of contents with you guys today and kind of see what we're up against. Let's take a look. We got chapter 1, 2, 3, 4, 5, 6, and then part 2, chapter 7, 8, 9, 10, 11, 12 chapters. Interesting. So the book is 12 chapters, 2 sections of 6 chapters each. Let's take a look at the first section here. Part 1, the theory, and part 2 is the applications. Chapter 1, the wave function. We got the Schrödinger equation, the statistical interpretation, probability, discrete variables, continuous variables, normalization, momentum, the uncertainty principle, and some problems. Pretty interesting. Chapter 2, time-independent Schrödinger equation. Stationary states, infinite square well, harmonic oscillator, algebraic and analytic method, the free particle, the delta function potential, bound states and scattering states, the delta function well, the finite square well, and further problems. Then we got formalism, interesting name for a chapter, Hilbert space, observables, Hermitian operators, determinate states, eigenfunctions of a Hermitian operator. What the? Read this sentence, bro. What is this? This is crazy. Hermitian operators go dummy. Discrete spectra and continuous spectra. Generalized statistical interpretation. The uncertainty principle. Let's go. Proof of the generalized uncertainty principle. The minimum uncertainty wave packet. The energy time uncertainty principle. Vectors and operators. Bases in Hilbert space. The Dirac notation. Let's go Dirac. Dirac is super cool. Changing bases in Dirac notation and some problems on chapter 3. Okay, first 3 chapters are hefty. And I remember when I first went through these 3 chapters, I had no idea what was going on here. And then chapter 3, formalism, kind of put everything together. It was very nice. Then chapter 4 is like your first real application of quantum mechanics. Quantum mechanics in 3 dimensions. We got the Schrödinger equation again. Travel back to this section, but I guess you slam it from the 3rd dimension here because it's quantum mechanics in 3 dimensions. We got spherical coordinates, the angular equation, the radial equation, and the hydrogen atom. So this entire chapter, I think, is focusing on the quantum mechanics of just the hydrogen atom. So you solve the Schrödinger equation for the hydrogen atom and a bunch of cool stuff pops out and you focus on it here. We got the radial wave function, the spectrum of hydrogen, angular momentum, eigenvalues, eigenfunctions, spin 1/2, electron in a magnetic field, addition of angular momenta, electromagnetic interactions, let's go David Griffiths, minimal coupling, the Aharonov-Bohm effect, Aharonov, Bohm effect, further problems on chapter 4. Then we got identical particles, 2 particle systems, bosons, fermions, exchange forces, spin again, generalized symmetrization principle, atoms, helium. Okay, we went to hydrogen, now we're doing helium. The periodic table. Okay, so I guess we cover all elements here. Solids, the free electron gas, band structure. And this is the last chapter, which I'm going to end the video off with. I'm not going to go to this second section because this is a Quantum Mechanics 2 course. I think everything up to chapter 6 is more than enough for 1 semester or 1 course for introduction. Let's take a look at it. Symmetries and conservation laws. An introduction, transformations in space, the translation operator, how operators transform, translational symmetry, conservation laws, parity, parity in 1 dimension, parity in 3 dimensions, parity selection rules, rotational symmetry, rotations about the z-axis, rotations in 3 dimensions, degeneracy, rotational selection rules for scalar operators, selection rules for vector operators, translations in time, the Heisenberg picture, time, translation, invariance, and further problems. So this is a crazy course. Like I said, I'm not going to go further on This is 268 pages of like crazy stuff, but it is a nice introduction. So like I said here, they give you a gentle, maybe not gentle, but broad picture, bird's eye view, overview of quantum mechanics. You're kind of introduced to it without doing any crazy math, I would say. It's more just like theory. And then here is the meat and potatoes. Here you solve quite a lot of things. You start with the Schrödinger equation, and then you solve and you figure out stationary states. You solve it for the infinite square well. You solve it for the harmonic oscillator in two different ways. The analytic method here is crazy. You solve it for the free particle. You solve it for the delta function potential and the finite square well. So there's a few examples here. Basically, the Schrödinger equation, you plug something in. What that thing is the potential of the system you're talking about. So stationary states is not a potential, but infinite square well has a specific potential. So it looks like this. It's a square. If you don't know what potential means in the scenario, don't stress about it. You get introduced to it here. But you plug this potential into the Schrödinger equation, you solve it, and then you get interesting information like stationary states and some other cool stuff out of it. So the infinite square well is one type of potential that you solve the Schrödinger equation with. The second one is the harmonic oscillator. It's pretty complicated, so they give you two methods of doing it. The third one is the free particle. Then you do it for the delta function potential, which is very interesting. Then you do it for the finite square well. So you have 5 different potentials that you slam in this chapter, and it's very difficult solving all of these, but you can do it, you get through it. And then in this formalism, you kind of take a break from solving problems and you look back, because in chapter 2, they basically take some of the stuff that you learned here, bird's eye overview in this first chapter, and they kind of force you to just solve using math and calculus. You don't really know what's happening, you're just solving things and getting solutions. But in this formalism, they kind of explain the math underlying what you just did here. And they introduce some new kind of interesting math that you maybe never heard of before. Hilbert space and stuff. Basically what you do here is you solve differential equations. So if you took some calculus, maybe you know how to do this. If you don't stress about it. You figure it out very quickly after doing a couple examples. But it is just calculus problems. Here, you get introduced to Hilbert space and all these other crazy things, which is very interesting because it kind of combines linear algebra and calculus together, and it combines this thing called operator algebra, which I don't know if it's a separate field of math, but you use it a lot of operators. So quantum mechanics kind of has 3 different kinds of math. You got calculus, all the differential equations and stuff. The Schrödinger equation is a differential equation, so you solve a lot of these problems using calculus and differential equations. You use some linear algebra, maybe not that much for solving problems, but it's very important to know because linear algebra kind of spews out some cool, interesting properties that you only know if you know some linear algebra. And this operator algebra is super helpful because instead of solving these problems with a lot of like calculus and a lot of crazy linear algebra, you solve it with operators, which kind of simplifies the way the math looks. It makes everything, takes a bunch of, maybe a whole line of math and compresses it down to like one symbol. So you're just moving symbols around and it's awesome. So this formalism is a big chapter. It is the foundation of the calculus. So here's the meat and potatoes, here is the foundation, and here is just some introductory material. It is still very important and it is very confusing, some of these things here, but this is a general introduction, maybe not too many actual quantum problems, maybe just a bit of like conceptual problems. Here there's a lot of problems, and in this formalism it's a whole different world. So once you get through this formalism section, I think you're going to be like, well, I kind of have an idea of what's going on here. And then they jump into an insane problem, the Schrödinger equation in 3 dimensions, specifically the hydrogen atom. Let me tell you guys, bro, solving the Schrödinger equation in this scenario, you do it for 1 dimension. All right, you're only dealing with the Schrödinger equation in 1 dimension. Here you jump to 3 equations and it becomes crazy. You basically split apart the Schrödinger equation into a couple different equations, the radial equation and angular equation, and a bunch of interesting stuff comes out of it. Stuff that you maybe learn in chemistry. So this is also a big practice chapter, and it introduces some other crazy stuff like spin, which nobody knows what it is. Cool. Then you kind of take a break and you talk about some other stuff, identical particles like I don't know, two atoms, what you could say about a two particle system. At this stage, chapter 5, I think you should feel fairly chill. There's not going to be too much crazy stuff introduced to you. Most of the crazy stuff is up to chapter 4. Here, I think you're coasting. And I think in an actual course, in a one semester course, you do chapter 1, 2, 3, and then you have a midterm, so maybe half of the course is done. Then you do chapter 4. Maybe you do a little bit of chapter 4 before the midterm, but I think chapter 4 is reserved for the final. So chapter 1, 2, 3 is the midterm. And then you do 4, 5, this identical particles, which is very interesting because you do the helium atom, the periodic table, and solids, and the free electron gas. So a lot of like macroscopic kind of chemistry, non-quantum mechanics things jump out of this. So you might connect it with some other interests that you have, and it's going to be very cool. So chapter 4, 5, and 6, this is symmetries and conservation laws. I don't know what to tell you about this. This is a whole other crazy chapter. I'm not going to talk about it too much here today. But that is the whole course overall. I'm just doing a quick summary here, just reading the table of contents, trying to see if I can remember what happened here. But what I remember is I really struggled with chapter 1, 2. Chapter 3 was really confusing, but by the time chapter 3 ended, I was like, okay, I kind of have an idea what the fuck's going on here. Quantum mechanics in 3 dimensions removes all of your confidence, and then you go through the gauntlet again. And then here I remember identical particles and symmetries. I was kind of chilling, not too bad, I don't think, at least. Then you do the final exam and you pray that you do well. So that is quantum mechanics introduction. I would say a first course if you take it, and then you could do applications. And like I said, this is the standard course, Introduction to Quantum Mechanics by David Griffiths. There are other books out here, but this is the one I've seen used in many schools. I'm going to put up a couple pictures of some other interesting ones here, but these are kind of advanced. But it's always nice reading. If you see something in this book that you're confused about, you can open up another book. All of these books you could probably find free PDFs online. Just search up Google, title of the book, free PDF. You should find it for free, no stress. And if you find all of them, you can cross-reference and try to see if some of your confusions get explained in the new book. Thank you guys for watching. Can't wait to start this quantum mechanics course. I'll see you guys in the next video. Peace.